Hello everyone. In this lecture, we are going to learn the ideal Brayton cycle, which is a base model of a gas turbine. Before watching this lecture video, I would like to recommend you to read the chapter 9.8 to 9.9 of our textbook. At the end of today's lecture, I really hope that you can answer these two questions. So the first question is, how can we calculate the each state of the Brayton cycle? And the next question is, how can we conduct the thermodynamic analysis of the Brayton cycle? So far, we have learned the spark ignition engine and the diesel engine. So even though they are a little different from each other, they can be categorized as one kind of type of engine, which is a reciprocating engine. Now, compared to those type of internal combustion engines, gas turbine is quite unique. Okay, so the difference is how they are operating. So for reciprocating engines, you should have pistons inside, and piston, as we discussed earlier, should move up and down. So it basically should have certain, more likely going up and down motion, more linear motion. And this linear motion is converted to rotating motion in the crankshaft. Okay, so that is a uniqueness of a reciprocating engine. Compared to those type of engine, gas turbine is connected through all one shaft. So we are going to talk about more details about how this gas turbine consists of in terms of components. But we have compressor and the combustion chamber and turbine. And those can be connected in one shaft. So rotating a compressor it also rotates the turbine. Okay? So basically, there's no need that we have to convert any linear motion to rotating motion in a gas turbine. And because of this unique feature of a gas turbine, it does have several very compelling advantages over the reciprocating engines. Then I show you a couple of advantages here as we see in this slide. Okay, so why should we use gas turbine? Why is the gas turbine very popular, particularly in several applications? Because gas turbines are very high power to weight ratio engine, meaning that it is really smaller than most reciprocating engines at the same power. We don't need a piston, and piston actually takes a lot of volume, and that makes all movement inside engine complicated. And in the same way, gas turbine has fewer moving parts and less vibrations. Again, these vibrations in reciprocating engine mostly come from the linear motion of pistons. But gas turbines do not have those pistons, so it does have very less vibrations compared to reciprocating engines. And as a result, gas turbines have high operating speeds. The RPM point of view, gas turbine is typically operating at around 10,000 RPM. But when you really think about how you run your car, how to drive your car, and when you really look at the odometer, the RPM of your car is usually around 2,000 RPM to 3,000 RPM. And if we can move to a very high RPM, but it cause a lot of vibrations, and you can see a lot of kind of noises from this operation. So we are talking about totally different rotating speeds regime between the reciprocating engine and gas turbine. So with this unique feature of gas turbine, we use those gas turbine engine in many different fields, but particularly we are using those engines for two main fields. One is in a jet plane, okay, and this one is what we usually see when you take a flight, right? And those gas turbines are kind of attached at both ends of your wings, and that is a gas turbine. Okay? And another very popular field of area that we use gas turbines are in power plant. Okay, and those, as you see here, that is a kind of good photo of power plants. And now you can see four chimneys here. and each chimney is connected to each gas turbine. So this power plant is 4 gas turbine power plant. Okay, and the gas turbine takes a smaller volume, but compared to the size, it does generate a lot of power. So that's why we love to use gas turbines in power plant. In our continuing lecture, I'm going to focus more on power plant. Okay, so then the question is, how can we generate a power by running a gas turbine? Okay, but this power can be simply considered to be a more likely propulsion power when you think about using a gas turbine for jet engines. But we are going to more talk about the power plant. Now, gas turbines are popularly used in jet engines or in power plant. But in what else applications can we use the gas turbine for? Maybe if you're crazy enough, then you probably can put your gas turbine in your minivan. Now let's try to look at this fun video. Now one very innovative engineer puts a helicopter gas turbine at the backside of a minivan, and now he's trying to test drive it. So 1, maybe 3, 2, 1. Yes, go. Okay, so we can use gas turbines for many different fields of area, as you have seen. Then let's try to see, how this gas turbine can be made of. Okay, what components are there inside? So that is quite schematic and kind of scenic through view of the gas turbine. And we should have certain inlet. More likely, we have a shaft that connects everything. Okay, and air is sucked in, to the gas turbine, and the air first meets a compressor. Okay, compressor, we have rotor and stator. So going through several stages of compressor, air is compressed to very high pressure. Then it meets the combustion chamber, okay, where fuel is sprayed out to the already highly pressurized air, and they make a kind of strong combustion to make the air and fuel mixture, or like a burn gas, to be at very high temperature and very high pressure. And this high pressure, high temperature burn gas hits the blades of a turbine to rotate the shaft. And this rotating in the turbine, basically connected with the shaft, also runs the compressor. So compressor all operation and power comes from comes from the part of power generated by the turbine. And the difference, the excessive power after we run the compressor actually should go to the generator, and this generator generates electricity. So that is how we make use of gas turbine to generate our power. So now, as you see, we have 3 main components. Okay, compressor, combustion chamber, and a turbine. You may want to see this video clip that I borrowed from his YouTube channel, and I'm going to give you a link in Canvas to watch this YouTube video. But let me show you how the very good explanation of how gas turbine is operated and where can this gas turbine be used. Please enjoy. So that is a generator. So, basically we saw more realistic features of gas turbines, inside, like how compressor and combustion chamber and turbine are connected together by one shaft, and run this shaft to generate the power, or drive certain liquid and natural gases and so on. But if you really make a simple schematic diagram of the gas turbine, then we can have that diagram. That is more likely how the gas turbine, realistic gas turbine should be operated and consists of. So we have compressor, and through the compressor we have fresh air now comes in, and now that is pressurized at high pressure. Then it goes to the combustion chamber, where fuel is mixed together with the air in the combustion chamber as well to make a combustion process. And now high temperature and high pressure burn gas should go through the turbine, okay, and it expands in the turbine to go to the exhaust gas. And the important thing is that this turbine is connected with the compressor through one shaft. Okay? So all this power that is generated by turbine runs the compressor, and the remaining part goes to the generator or somewhere to make a net work or net power. So that is how actual gas turbine works. But again, that includes combustion process, which is already very complicated. Okay, and it does have change of your combustion, your working fluid from fresh air and to burn gas. Okay, so if you really look at how the real gas turbine operates inside in terms of as a category of internal combustion engine, that is pretty complicated to do certain thermodynamic analysis. So we do need to do certain simplifications. So that is a more simple version, and that is basics of the ideal Brayton cycle. Now, this cycle, from its name, was invented by Brayton, okay, an engineer. And this Brayton, the person, actually thought about really simple version of thermodynamic cycle, which is comprised of compressor, turbine, and two heat exchangers. So when we try to use the ideal Brayton cycle, we don't care about the combustion process. Instead, we think the combustion process as a heat addition process. And now, after going through the turbine, the burn gas is just going out to the environment in atmosphere as an exhaust gas. But instead of considering that exhaust process, we assume that there is one more heat exchanger where heat rejection process occurs. Okay? So now, entire ideal Brayton cycle doesn't consider the fuel. Instead, we assume that only air is the working fluid of that ideal Brayton cycle. Okay, so no combustion, just a heat addition process instead of combustion. And instead of exhaust process, we have heat rejection process. That is why we have those processes in the ideal Brayton cycle. But the way the turbine runs in connection with the compressor to produce a net work still remains the same. So how can you make the ideal Brayton cycle? So we already talked about certain simplification that we have to consider when you deal with the ideal Brayton cycle. But at the same time, we have to consider that your compression process is also ideal. And turbine, the expansion process in the turbine should be also ideal. Okay. So now, in the next slide, I'm going to move on to my iPad and using a stylus to explain, how we can set up, 4 basic processes of the ideal Brayton cycle and how we can do thermodynamic analysis for each process.